everyone. First of all, I would like to, on behalf of the committee, thank everyone for the excellent participation and also all the great talks. I think it's generally a reflection of the great work we've done. And I just kind of go to the next slide. Great. So yes, I think we had excellent participation so far. There's lots of great attendance, and it lasted until now. I'm very happy to see this. And hopefully, I think this is a suggestion that okay, so it's not me, okay, right. So we do long for like a community like this, right? So I'm hoping this is a great starting point for us to form a community that we can keep discussing things offline after this workshop. Just so that, this is a summary talk, but of course I will not be able to give a complete summary. I'm not AI. This is just from my personal perspectives, right? I want to just tell you guys what we learned, and hopefully I'm hoping that you can also share yours at the end of my talk, and so we can have these discussions, what we learned so far. But just also maybe a little bit more about myself, right? So I am a physicist, but I have actually had 10 years experience working on FPGA implementation so far. But because I'm a physicist, I wasted most of the 10 years attending users meetings and doing actual physics. The rest of my time, I think so far, from my personal experience with FPGA, I seem to think there are some limitations with it. First of all, for HDL and languages, rather, it seems to be a very steep learning curve. And for example, for myself, it took me really a solid year to actually get used to comfortable working in HDL and be able to do things efficiently. And I think I speak on behalf of lots of students I encountered in physics trying to work on FPGA. It does seem like it takes a long time for us to get used to it. And another thing is also from the firmware development point of view, it seems to be very time-consuming, right? There are lots of steps before you can actually go into implementation on a hardware chip. And also, I think my biggest complaint, and there are also other reasons, but my biggest complaint is actually the long compilation time it seems to take in the routing and placement optimizations. And especially for me, because I work on tracking, which is quite complicated algorithms, we actually spend lots of time dealing with timing issues. I have a link here to this talk, which can do some of these similar things with what we might personally encounter. So these are things I typically struggle with. I do think I seem to recall there are some talks I think actually seem to help actually to address some of these issues in that direction. So, I'm going to start with just from the HDL language point of view, right? I think, this is not news, right? We have Xilinx has been also aware of this issue and actually has, uses C2 HDL in particular, which high-level synthesis, and this has been in Xilinx for 10 years now, I think even more than that. However, I think we actually use this in the track trigger firmware that we developed. However, I think we still have a learning curve even for HLS, right? It's still a bit different from C++ and also HDL. So even from both perspectives, I think we do have a learning curve, but it's much smaller, which is good news. But also there's some limitations still left, right? I think in general it can be slower and also maybe less control over some of the memories. And there are quite a few talks, I think I'm linking some of this here in this conference that use HLS, right? So I'm just linking here as a reference. In addition, I think there's a new talk actually on the bond machine, which is a completely different architecture. And I think the bond machine actually now also support to enable these bond machines from the high-level languages, which is also quite nice. So that's all I want to say for HDL language alternatives. But then from the timing perspective, I complained about the compilation time. And I think I'm actually very happy and surprised to see this talk here that basically they achieved this impressive 15 seconds to fully place and routed circuit. Where are you when I was struggling with timing? However, this will not solve my problems apparently because first of all, it's very preliminary, and also it's actually not for algorithm-intensive applications. So, like for my perspectives, unfortunately, not yet. And also, they did say that routing remains a very challenging problem. And I understand, right? There's a reason we haven't been able to improve for a very long time, like the speed of the FPGA firmware compilation. But I'm hoping it's a great start. I'm very happy that industry people are thinking at least that this is a problem and they're trying to improve, even though it's very hard. And I understand it's very preliminary, but I'm really hoping in the maybe far future that I actually see Xilinx get into this and actually develop a tool that says 15 second to bit file. So that's one of it. And another thing is, I think, of course, long combination times, we cannot easily fix it. But one way we can maybe, make it a little bit easier is for have like better verification and monitoring tools in general, so that we don't take this many iterations of trying to compile the firmware. And for that, I think there are a few things that I find particularly useful, like firmware verification. I have a little slide for this. I think there's something a lot of us probably heard for the first time, and we probably will go right after this meeting to try it out. And then also we also have this UVVM, test benches in general. Of course, I think verification, firmware verification is not going to replace that, right? And we still need test benches, so it's good to have some general things we can all use. And also another thing is spy buffers, right? So fast monitoring on FPGA. So if you actually have to go to, because simulation cannot simulate everything, right? There are still things like, for example, the CDC, you really don't simulate well in a test bench. You do want to test on chip. And when that happens, I think the spy buffers can actually be a very useful tool to debug things on chip. So starting with formal verification, we actually have 2 talks today. I wrote this kind of right before this, and, but I do think this is like probably my biggest take-home point. My first time really learning about this. I heard this very tiny bit a long time ago, but it's a very powerful tool. And we just learned this morning, like 2 talks ago, and there's an open source option right now. I think that's really what makes it possible, cost-wise. And then it sounds like there's some limitations just from talking to some people. I think some people did reflect that it took them some time to get into work. But now we actually have all these great tutorials, so I don't think this will be a problem anymore. And then I just learned also from Nina recently, right, that there's apparently special lessons to the commercial option given to the open source project, which we contact them. I'm very happy to hear that because Apollo is open source. And so there are 3 talks, I think, on this topic. 2 of these are like just on this, and I think the third one, the Colibri, are actually a use case, right? Like they're using this with I think, continuous integration. All of them, I think, actually contain some tutorial on how they set this up. So I think you should all check it out. I know I will. Again, right, I think we all agree that this should become a common practice now that we can get these open source options for free. I do think it's really a milestone for the firmware verification. Okay, moving on. So that's all I want to say in terms of my concerns on FPGA implementations. But moving on to more observation of the conference. I think we all recognize, right? I mean, there are lots of duplications and small things we implement that we kind of want to maybe reduce these duplications and like avoid reinventing the wheel. But in the process, unfortunately, I think independently we invented lots of frameworks and tools that are kind of do similar things. But I do think the fact that we have developed so many frameworks shows that we do recognize there is a need and a problem for these things. I'm hoping this community building, the fact that we're all talking to each other now, these independent developers, maybe can help us consolidate some of the options and make them into a better, more uniform platform. So I'm really hoping we can get this discussion started, maybe starting from the forum I'm making here. So I'm just linking a bunch of talks, and there are actually more, and you can but there are also quite a few different things that are also a lot of them are very well implemented. I'm telling you, and then they're very rigorously tested. However, there's just so many of them. They do similar things, which is unfortunate waste of person power. So let's hope we can consolidate from now on, so we don't waste more of our independent. What am I doing here? Oh, is this guy? Okay, but then I do have, okay, sorry. So I do have another perspective though, and maybe this is not something we talk too much in the talks, but just by discussing with people in general, also my personal kind of feeling maybe before this conference is that, I'm already experienced HDL developers, all these small things that we're saying that, we have common implementations. I already had my own version, I use it all the time, why should I switch to a common framework? It's actually going to take me more time, right, to adopt something that I already have locally. I just work on this, I can work on it for 10 years from now on. I can use the same thing, I work on things. This could be more efficient for me. But I think there are a few good reasons why, even for experienced HDL developers, to adopt a common framework from now on. One, I think, is to reduce the learning curve, not for you, but for beginners, right? I mean, you will have students, right? You don't work on alone, hopefully most of the time. I think the students in general, when I talk to people using HLS or other common firmware framework, experienced HDL developers seem to think this is harder than HDL. I mean, I agree. But I think for students, I mean, all the feedback I got so far is that they think it's much easier. They're so happy they have this, and this is much better. And I think I also agree with them. So in this case, I think just so that we can have more people in general to work on a PGA, this is a good thing to adopt common framework, but also to expand your horizon, right? I think we all have our preferred ways of implementing code, but we may not look at other people's code until we were forced to, but in this way, we can actually have the opportunity to learn different practices or approaches that we may not think about ourselves if we don't have this opportunity. But also, this also opportunity for you, for us, to really improve the existing framework with our expertise, because I'm pretty sure you look at it for you like, actually there are things I have these tools for this, and you don't have it here. But instead of just like not use it, maybe we can just also contribute and then make a better common framework together. So that's, I think, my thoughts on the common framework and tools. Moving on to just some other exciting things I think we kind of did a lot in this conference. For example, machine learning algorithms, right? I think we had quite a few talks on machine learning algorithms. And there are actually two, I can separate into two things. I mean, first of all, I think we all know as its point, for machine learning to work on effective algorithms, I think pruning and quantization are the important 2 points, right? I think a lot of people touch base on these 2 points. And we actually had, I think, 3 different common tools that are presented HLS from, so if you actually click on the link here, from implemented in HLS, and the conifer, which is implemented in HLS of HDL, and also the deep learning processor, which I believe is HDL by MathWorks. And then we also have so many different specific applications using some of them even using the tools that's presented here. And maybe just special shout out to the last one. Why is it? Okay, special shout out to the last one, which actually showed us machine learning application on IPGA in the medical field, right? I'm RI. I think lots of people say like this is a great talk. It was very impressive. They were able to achieve less than 3 minutes network training on IPGA, I think. Okay, so moving on, I don't have much time to talk about all the topics, of course, but just to maybe mention to some other interesting topics. And one thing I think particularly interesting for me, because I'm a physicist, I struggle with Monte Carlo samples all the time. This MAT graph on IPG, and I really like this idea, right? I think it's a great project. I'm just showing you some result here that they mentioned in the talk, right? Like it's like 14 times faster than GPU, a lot much faster than CPU. But I just want to mention this is actually very, very right. I think the speaker sector told me offline that he only worked on this for 3 months. Right, this is his first talk in the conference. I thought he did a very good job. Right, I'm hoping that in the near future, or maybe a year or two, maybe you can come back with the full result and a MAT graph simulated with all the interesting physics process on PGA and in the paper. Right, and. Then also another thing I think we kind of decided to cover a little bit is the quantum applications, right? I mean, I think we all want PGA to have as many applications as possible, and quantum computing is something that we're hoping maybe they can scale up, and then it's very good news for us that they can actually use FPGAs for radar and control of qubits either in the sensor or the computing part of the application, and they're actually very cost effective. So I'm very happy to hear that and see that there are very active development on those areas. Of course, as I said, there are so many great talks, and but these are all the ones I want to cover. But because there's so many great talks, actually we are decided to actually select the best talk with a surprise gift. And I'm sitting here. So with this, and we're looking for young speakers in general, right? So no offense to the more established people out there. So we decided to actually there are 4 nominations just to get this conversation started, right? I think there's Alberto Pero that did the Colibri talk, and also the Mattia Ricci on the hardware acceleration. This is the MRI talk. I think the Anna Margarzata Kulinska this morning actually on the hardware compiler, and also Nina Engelhardt on the formal application. And suspense. We decided to give Nina. All right.
Thank you very much.
Yeah, thank you, Nina. Should we take a photo or something? But well, okay. All right. Thank you so much, Nina. I think the reason we selected Nina was because I think this is something like, as I said already, right, this is something that really opened, I think, a lot of people's eyes on something new. I think possibly, like a milestone in terms of FPGA algorithm verification, in my opinion, right, because you're able to give us this open source tool that we can now use for this. So thank you so much for this talk. I think with that, that's it. And I would like to hear if you have opinions or any things you want to share with us. I would be very interested to hear. Thank you.